All right, so 16, I'll just say it again so it's on the recording. This is a horizontal reflection over the y-axis because the negative is inside the parentheses, and this is the vertical reflection over the x-axis because the negative is out in front, okay? In 15, we're given a parabola. Now, this parabola has already undergone some transformations, right? Because the parent graph would just be x squared. So, that being the parent graph, we've already undergone some changes. Describe the three transformations which would transform the graph. Give both the transformations and the order. So when you describe it, just describe it in the proper order. What would come first, McKenna? Not yet. Not yet. Someone help her out and tell her why. Mason?
Go right 8.
Okay, now how did you know that that right 8 came first? It's in the parentheses, right? It's within the parent function, like it's within what was being squared. So, and horizontal stuff is always going to come first because it happens within the function. So order of operations says that has to happen first. So it's going to be a shift right 8 units. And what's next? Isaiah.
Then would it be
Raise your hand if you agreed that you go up 5 units next. Raise your hand if you disagree. And why, Jordan? How did you know that came first, that negative out in front came first? You just did. Who can verbalize how they know that that negative needs to be applied before the plus 5? Isaiah? It would be a completely different graph, but how do you know that that negative comes first? Yes. Cameron, add on to that. Yeah. Right. It's order of operations. So think about how you would go through simplifying if you knew the value of x. You would subtract 8 first, and then you would square it, but the square is a part of the function. Then you would negate it, and then you would add 5. Order of operations. So the negative out in front is a vertical reflection over x-axis. And then we'll get to Isaiah's shift vertically up 5. Any questions on that? Okay, we're going to skip 14 for now just because I want to get to some other topics. We've been doing transformations for a couple days more recently. 13 changes our focus to inverses. What's the key concept with inverses? Not opposite. I want to stay away from that because opposite really truly means to negate it. And I don't want people to do that. Reflection over the... You do reflect... Perfect. That's one key concept. It's a reflection over the line y equals x. What's the big overall... What switches? X and y. You switch the x and the y. So, here's our original function. Graph the inverse. Well, we need to kind of figure out what each of these critical points are, and we need to flip them. So, if I come up with these coordinates, negative 1, 2, 3, 4, 5, 6, 7, negative 1, 2, 3, 4, 5, negative 7, negative 5 is going to flip to negative 5, negative 7. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. I mean, here's a pretty good one. You always want to take a look at your x-intercept as well. That's negative 2, 0. So where are we going to go? 0, negative 2. Nice job, Bo. Your y-intercept is another good point. Our y-intercept is 0, 2. So when you flip that, that's 2, 0. This corner point is critical because it's kind of turning, the graph is shifting right there, so that point is 1, 3. We're going to go to 3, 1. And the last point here, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. 7, 5 is going to go to 5, 7. Do you see the symmetry that we're supposed to see? Good. And label these graphs. This one's f of x, the one that they had for us. And then ours is f inverse of x. Now, what is the range of f inverse of x? Range, lowest y value, is what? -7. Highest y value? 7. So the range is -7 is less than or equal to y is less than or equal to +7. And f inverse of -3. Since we've already taken the time to graph the f inverse, let's look. When you input a -3, 1, 2, 3, what's the output? -5. Okie doke. Number 12. Is this function a one-to-one function? Remind me, if you can. I'm sure there's several of us that forgot, but tell me, impress me with what you remember about a one-to-one function. Somebody. What makes something a one-to-one function? First of all, it has to be a function in and of itself, so it needs to pass the vertical line test. Second of all, its inverse also has to be a function. So the inverse needs to pass the vertical line test, which means the original needs to pass the horizontal line test. So does this pass the vertical line test and the horizontal line test? Some of you are like, how am I supposed to know? Pick up your calculator. Graph it. So it's y equals, and actually we're going to have to talk about whether or not we know how to find the absolute value symbols. Okay? I'm going to assume that some people do not. Everyone's calculator has a math button right here. If you hit that math menu and then scroll over up top just one to this NUM, which stands for number, the first option is going to say abs. That's the absolute value. So if you hit that, it opens up absolute value signs. X minus 6 plus 2. Graph. Does this pass the horizontal and vertical line test? No. Explain. It does not pass horizontal line test. We'll just say that. I'm also going to take this opportunity to talk about the parent graph of an absolute value function. It's kind of like, and so I just typed in on my calculator, absolute value of x. Cameron, get your head up, please. It's kind of like the parent graph of a quadratic. It has a vertex. There it is. Okay? Look up at the board here. That's the parent graph. 0, 0, it's just kind of a V shape. That's what absolute value graphs are. What transformations happened to this to become this? What transformation happens first? Lydia? That's not to the right, but you're on the right track. Maggie, help her out. 6 to the right. We got to start inside. That's horizontal. 6 to the right, and then 2 units up. Take a look. 6 units to the right, and then shifted 2 units up. So the vertex was 0, 0, But now after being shifted 6 right and 2 up, the vertex is now 6, 2. Yes? It's going to keep coming up. When we do every additional parent graph you learn, there's going to be transformations. Good. This one is just simplifying. Can I skip that? Distributing and combining like terms. Okay. The inverse function is given to you in number 10. They give you the inverse function. They're asking you which one's the original function. How can I do this algebraically? What do you do to write an inverse? Kirsten. Very good. We switch the x and the y, and right now this is like y. So I would write x equals negative 3/4 y plus 2. Then what, Aiden? Right, we're solving for y, generally speaking, so specifically, subtract your 2 first, and then Nathan C. Right, multiply by the reciprocal, negative 4/3 on both sides. Now on the left-hand side, I just then had to insert my own set of parentheses because that was a binomial. And you have to make sure you distribute that. The negative 3/4, negative 4/3 cancels. And then when you distribute, we get negative 4/3 x. And negative 4/3 times negative 2 is how many thirds? Negative 4/3 times negative 2 is blank thirds. What's negative 4 times negative 2? 8 thirds. Plus 8 thirds. So our answer is what is it? 2. Careful, because they're all super similar. Now let's pretend we forgot how to do that. Because we know what inverses are supposed to look like compared to each other, there's so many ways on exams you can use your knowledge and calculators to sort of cheat a little bit. I mean, this would be kind of trial and error because you'd have to check every single one. But if you type in the original inverse function and then type in kind of guess and check, type in each of these and look at it side by side with that one. So I'll type in what I now know is the right answer. What should it be the case here when I look at the two graphs? They should be symmetrical over y equals x, right? So is that a line of symmetry? Yes, okay? And on the other 3, it probably won't be. Now, it's a little bit dangerous because some could look, sorry, I'm going to remove that because I just wrote on my screen. It might be a little dangerous because some might look like they have that symmetry. You got to be careful, but at least it might get rid of a couple, process of elimination for you. 9 is a transformation. 8. Oh, 8's a great one. Okay, it's a transformation question, but you may not have seen something exactly like this before, which unfortunately or fortunately is the position you're going to be in on the Regents in June. You've got to use the skills that you've been given. So let's think about this. Given this function, okay, it currently has an x-intercept at -9 and 3. So if I want to quickly sketch a graph, it's going to cross at -9 and 3. And if you want to fully wrap your head around what's going on, again, use your calculator, type this in, just so you can have a quick sketch in front of you. So there it is. It's this parabola. We're kind of missing the bottom of it, but it's crossing at -9 and 3 currently. Yes? Any questions? Just to wrap your head around it. Where does this function have x-intercepts? So look carefully here. What changed from the original to this one? What changed from here to here? They took out the x and replaced it with 3x. Everyone look up at the board. So if this was your f of x function, they took out the x and they replaced it with 3x. Do we see that? What's the transformation then? What does multiplying, doing and plugging in a 3x do? Dilation, which direction? Horizontally, stretch or compression? Compression by a factor of 1/3. The reciprocal of 3, 1/3. So these 2 points are going to squeeze in 1/3 of the way. So if -9 squeezes in and is now only 1/3 of the way, what coordinate is that? -3. And if this squeezes in only 1/3 of the distance, it's going to be 1. So everything just got squeezed in, so those x-intercepts are now -3 and 1, option 4. Let's take a peek at that. If I take this and do it side by side, I go 3x squared plus 6 times 3x, and this isn't necessary, it's just kind of hopefully enhancing your understanding of what's happening. Watch where this graph shows up. Here we go. There we go. Everything got squeezed in. Now, I am missing the bottom of this graph. What do I need to adjust on my window so that I see the vertex? What do I need to change so that I see the bottom part of the graph? Y minimum down to, let's say, -30. Will that be enough? Nope, not enough. It's still off. So go back to your window. All right, if that's not enough, I'll really try to kill it and go to -50. Is that enough? That's enough. And then we're going to squeeze in by 1/3. Good? Okay. Number 7, back to that absolute value function. Remind me, here's the parent graph. Where was the turning point of the parent graph? Do you remember? 0, 0. Yep. Which transformation do we address first? Nathan H. Eight right, perfect. So when we shift 8 right, where's our vertex now? It was at 0, 0. I'm shifting 8 units right, so what's the new coordinates? 8, 0, okay. From there, where are we going to go? What's the next transformation? Fred. Well, is it vertical or horizontal? Vertical. So that affects which coordinate? Vertical. You move stuff up. Y. Yeah, good. So I'm going to take my y coordinate, which is currently 0, and I'm going to multiply that by 1/2. So you're still at 0. So actually, if you're at this point and you compress vertically towards the x-axis, well, you already were on the x-axis, so you're still on the x-axis. So that actually didn't change anything. And then we are shifting it up 3, which again is vertical. So when we move it up 3, we're moving our y coordinate up 3, and we are at 8, 3, option 3. 6, keep going backwards, is a 2-second question. What's the answer? What is it? Everybody? 3. That's just a fact, a memorized fact. Nathan kind of started the day by reminding us of that with inverses. Which of the following is the inverse of this? We already reviewed, switch the x's and the y's, solve for y, so now we'll keep backing up to the front. This is a great one. Number 4, compositions of functions. We haven't done this in a couple days. They give us the f function equation, but not the graph of it. They give us the g function's graph, but not the equation. That's fine. Okay? So this is going to force you to make sure you can evaluate function notation on graphs and on equations. So we start on the inside with g of 2. So looking at the graph, take a minute, try to figure out the value of g of 2. What do you think it is, Jake Hutchinson? G of 2, just G of 2 for now. 4. So here's your x-axis. You got to kind of find your origin first. But G of 2, 1, 2 is 1, 2, 3, 4. So now this is a 4. So we have to find f of 4. And now we have to plug 4 into our f function. 4 squared, 16, plus 2, 18. Done. Good? In which of the following 4 graphs is the output not a function of the input? In other words, not a function. Which one's not a function? Very good, Fred. 2. Fails the vertical line test. Exponent rules. When you're dealing with exponent rules, remember 3 things. No parentheses, no common bases, no negative exponents. Then it's simplified. So the first thing we're going to have to handle is the fact that this set of parentheses is being cubed. What is a negative cubed going to be? Is that going to be a negative or a positive? Still a negative. What's a 2 cubed? 2 times 2 times 2? 8. What is x squared cubed? Power to power rule says multiply, so x, or 2 times 3 is 6, so x to the 6. That's our first, so we've gotten rid of the power to power. And then we just multiply coefficient by coefficient, negative 40. When you multiply common bases, x to the 6th, x to the 4th, you add the exponents, x to the 10th. Option 1. Okay? Finish this for homework. And I have to give you your spiral. There wasn't one. Was it on your phone? I wonder if it was a glitch because you were looking at it on the computer. I'll double check that. It should be the same way. Okay.
Well, yesterday, the day before yesterday,